So now we've come quite a ways. We've developed the theoretical background for understanding why delta H is the key to differences in phase transition temperatures, boiling points as well as melting points. And we've related delta H to the strength of intermolecular forces within a compound. We've also explored how intermolecular forces are ultimately related to and can be predicted from molecular structure, including three-dimensional structure. Now what we're going to do is work backwards. Starting with a structure, how can we predict the dominant intermolecular force of the corresponding compound? And once we have those intermolecular forces, how does the impact of those IMFs on delta H influence phase transition temperatures? We'll learn a systematic process for answering these questions in this video. The first thing to understand is that intermolecular forces do affect phase transition temperatures. We've seen that delta H for a phase transition, for vaporization for example, affects the temperature of the transition, for example, the boiling point, and this applies equally well to the transition between solid and liquid. Stronger intermolecular forces in the more condensed phase are associated with a greater delta H value for the transition, which means higher transition temperatures from solid to liquid, and especially from liquid to gas. So the liquid to gas transition, as we've seen, completely destroys intermolecular forces between particles. But it's important to appreciate as well that the solid to liquid phase transition also disrupts intermolecular forces, because in the solid phase, where molecules are arranged very close to one another in a regular lattice and are not moving very quickly or really at all, they may be vibrating in place, but that's about it. And going from that to a liquid where the molecules are still in contact but somewhat randomly dispersed, now the molecules have more kinetic energy, and so intermolecular forces become a little less important relative to, for example, the solid phase. This random dispersal of the molecules in the solid to liquid transition does disrupt intermolecular forces. So in both of these transitions, from solid to liquid and liquid to gas, we're going from a more condensed to a less condensed phase. There's a disruption of intermolecular forces, and delta H is greater than 0. To predict the relative temperatures of a phase transition for, say, two different compounds, what we really need to know is the relative strengths of their intermolecular forces. If we can deduce that, we can deduce their relative temperatures of the phase transitions directly. And in fact, there's a direct relationship here. The stronger the intermolecular forces, the higher is the phase transition temperature. What are the relative strengths of the intermolecular forces? And can we find any general trends? Well, we've alluded to this a little bit already. There are general trends in the strengths of the intermolecular forces that are rooted in Coulomb's law. Remember, we said we distinguish the forces by the extent of the charges, whether they're full ions or partial dipoles, as well as whether they're permanent or temporary, which isn't quite built into Coulomb's law, but will influence, for example, the average distance between molecules with a dipole at a particular moment in time in the case of temporary dipoles. Really, the key at the root of it all is Coulomb's law, which by now, hopefully, is an idea that you're used to. Coulomb's law being very important for chemistry in general. So here are the IMFs from strongest to weakest. At the top of the heap, the strongest intermolecular forces are ionic bonds, and there are some who would say we can't really even call these intermolecular forces at all, but I like to lump them in here since they are electrostatic interactions between charged particles, which is the essence of intermolecular forces. Next come ion dipole forces, for example, sodium chloride in water, hydrogen bonding and dipole-dipole forces, dipole-induced dipole forces, which are somewhat weaker, and then London dispersion forces are the weakest of all. What we call the dominant or the major intermolecular force in a compound is the strongest one within it, and this is the one that dictates physical properties of the compound, and so we want to look for it first. In other words, if we know, for example, that a compound engages in hydrogen bonding with itself, then the fact that it engages in London dispersion forces is essentially irrelevant because the dominant intermolecular force in that compound will be hydrogen bonding. So when looking at a compound to determine how its intermolecular forces influence physical properties, start at the top of the list. Look for the possibility of ionic bonds first. Then look for ion dipole forces, then look for hydrogen bonding, then dipole-dipole forces, and so on and so forth down the list. Let's talk now about comparing melting or boiling points, these phase transition temperatures that are a direct consequence of the intermolecular forces. Step one is to identify the dominant intermolecular force in the compounds you are comparing. Let's say you're comparing a pair of compounds. You got to identify the strongest intermolecular force within each compound. With those in hand, then you order the two dominant IMFs, say there are only two, from strongest to weakest, which is stronger and which is weaker. Because the phase transition temperature is directly related to the strength of intermolecular forces, when you order the dominant IMFs from strongest to weakest, you've already ordered the compounds from highest to lowest melting point or highest to lowest boiling point. Pretty straightforward two-step process. Let's practice this in an example. So let's compare, for example, the boiling points of CH4 and H2O. Step 1 is to identify the dominant intermolecular force in each compound, and I'm just going to go down the list. So CH4. CH4 is a covalent compound, no ions within, so ionic bonding is out. It's not a mixture, so ion-dipole forces are impossible. Dipole-dipole forces, well, that depends on whether the molecule has a permanent dipole moment. The exhaustive way to do this is actually to draw out the three-dimensional structure and verify whether the molecule has a dipole moment or not. So if we draw out the tetrahedral structure of CH4, what we find is even if there are slight bond dipoles from H to carbon, the positions of these four dipoles in space are such that they're all canceled out. CH4 is a nonpolar molecule, so dipole-dipole forces are out. It's not a mixture, so dipole-induced dipole forces are out. There's nothing polar in a sample of CH4, and so the only thing left, the only force left for CH4 to engage in is London forces. And London forces are the dominant intermolecular forces in CH4. Now let's repeat the process for H2O. It's not an ionic compound, so ions are out. We're not looking at a mixture, so ion dipole forces are out. Water does contain OH bonds, and it contains an oxygen with a couple of lone pairs. That means that it can engage in hydrogen bonding, and this is the strongest force that H2O can engage in. Once we've identified that water can engage in hydrogen bonding, we've identified the dominant intermolecular force, so we can stop. While it is true that water engages in, for example, London forces, those will be irrelevant to the physical properties of water because it's the strongest intermolecular force that dictates the properties of a compound. Next, we order the dominant forces from strongest to weakest. Based on Coulomb's law, and from what we've just talked about, we know that hydrogen bonding is going to be stronger than London forces. And from here, we can simply write out to the side, for example, that H2O will have the highest BP, the highest boiling point, while CH4 will have the lowest. This method, by the way, works for any number of compounds. As long as they have distinct dominant intermolecular forces, you can order them from strongest to weakest forces, and you'll have the highest transition temperature to the lowest transition temperature right there.